we are talking about today is how transformers work. Now, we got a very quick run through with it, first lesson on this chapter. Just, primary coil, magnet, secondary coil, produces magnetic field, current transfers from one to the other. Cool. Okay. Now let's look at that into a little more detail.
Now we're looking at that subclass.
So we talked about this before, or at least it was mentioned last class, that transformers only work with alternating current. But why is that the case? Well, the primary coil has an alternating current flowing, making it an electromagnet, okay, and produces an alternating magnetic field. That's the key to how the transformer works. It needs this magnetic field that changes one direction to the other. So the core transports this alternating field around to the secondary coil. So here's primary coil. Here will be the fingers. Core. So this is an electromagnet, produces an alternating magnetic field going both ways, and then transfers that to the secondary coil. Okay? Now, the secondary coil now has, conducts in a changing magnetic field, so a current is induced in the coil.
Where is it coming from that line?
It's coming from this one. So I can't actually, So that's why it uses a alternating current. Now, what would happen if it was a direct current? So it's working. If a direct current is used, there is no output voltage, okay? Because the magnetic field produced by the primary coil is unchanging. And in order for the secondary coil to have the current and voltage induced into it, it needs that alternating magnetic field. So this is because magnetic field produced by the primary coil is unchanging. So with an unchanging magnetic field in the secondary coil, no voltage is induced. So you need that alternating magnetic field in order to induce voltage into the secondary coil. Yes. Direct means it goes one way. Yes. Alternating goes both ways. You need the alternating magnetic field in order to induce voltage in the secondary coil. That's what you need.
Oh, is this what we were doing the questions for before?
Yeah. So here we have our changing primary current. Okay, here's our primary coil, so it's going around. Produces a magnetic field in the core going both ways. There's arrows this way and that way, right? So it's an alternating magnetic field, which then induces a voltage in the secondary coil, which is also going to have an alternating current. And then goes to whatever. In this case, it just had a load of some sort of motor or something like that. You with me so far?
Yeah.
Anna?
Mm-hmm.
Yeah? Sylvie? Hamza?
Yeah.
Kate?
Wait.
But I need to fix this.
Could you print this
The best
out?
part, this is going to end up in the video.
Is it?
Yeah. I've done it a couple times already.
Can't you?
I can. I don't want to.
So are you like advertising their...
No, I can remove it from that.
You're advertising.
So, to answer your question, yes, I can print this out. I think you asked.
Print the cake.
You usually ask.
Well, then I want us to draw that.
No, you won't.
Oh my god, really?
Okay.
You didn't ask that.
So calculating current. Okay. So to transmit a certain power, we can use a small current as long as we have a high voltage. So the formula for electrical power, P equals IV. I being current, V being voltage, P being power. So for example, a power station generates 500 megawatts of power. What current flows if it transmits this at 50 kilovolts. Okay?
Kills the volt.
No, kilovolts.
It'd be cool if it was called killer volt, but our word kills the
So
volt.
we have 50 kilovolts, okay, and 500 megawatts. So we need to figure out how much current is going to be in this system.
We have to divide stuff.
That's P equals IV, right? Use that formula each time.
So P equals IV. But here I need to solve for, yeah?
I did the two dice.
So in order for me to find the current, okay, I need to rearrange my formula here. So I is actually equal to P divided by V.
It's not calibrated.
It's off a little. So here we have what you need to do. So P equals IV, we rearrange it to get current is equal to power divided by voltage. So 500 megawatts is 500 followed by 6 zeros. So that would be 500 million watts. Okay. 50 kilovolts, is 5 followed by 3 zeros, so that would be 50,000 volts. So I just take my 500 million divided by 50,000, and I end up with 10,000 amps.
So M means 6 zeros.
Yeah. M is 6 zeros, K is 3 zeros.
Oh,
Wait.
okay.
Which, if we remember from math class, changing units, the only one that wasn't there before is mega. So that's just 6 zeros. So now that you've seen this, I want you to do the same thing except 1 megavolt. So what would the current be if we had 1 megavolt instead of 50,000 volts?
20. Wait, one megavolt is 500.
No, 1 megavolt is 1 times 10 to the power of 6. Which is
That's 1 million volts.
That's a lot of volts.
1 megavolt is 1 million volts.
Yep.
So
So how many amps would be in that system?
100,000.
Yeah, I cannot.
I don't get it.
Okay.
Wait.
How much current?
50.
So the wattage is still going to be the same. It's still going to be 500 megawatts. But now I'm saying, what if it was transmitted at 1 megavolt instead?
Instead of 500 megavolts.
Instead of
It'd be
50,
doubled. Oh, instead of 50.
50 kilovolts. That's 50,000 versus 1 million. Very different numbers.
Okay, wait. So we have to multiply the answer by.
500 million by 1. I didn't have my calculator. Sorry.
So 500 million divided by 1 million.
Is it 500?
You can't solve that without a calculator?
Is it
I know.
500?
I know.
The answer is 500.
500 amps.
Remember, if you have 500 million volts
Yeah.
divided by 1
Hey, you just
million
gotta take the
volts,
zeros out. I
it'd
know.
be
I was
500.
joking.
Wait. I am confused. How did you do all that?
Magic.
Yeah, because we knew it was 1 million, right? So you just do the same
Oh, all
thing.
these megavolts and kill
Can't we just
things.
a simple like voltage?
Divided by is it 500? Oh yes, it was. Okay.
Because they're both mega units, right? Megawatts, megavolts. You can just take the mega out, and then it's 500 divided by 1, which is 500.
Oh, that's cool.
So you notice how much bigger of a difference in amperes from here to here. 10,000 amps versus 500 amps.
What's better?
Well,
500 amps, because if you're transmitting this power from, say, a power station to your homes, right? If you transmit it at 500 amps, there's less loss of energy.
Isn't it?
Because remember, we talked about if you have a higher current, then the wires get hotter and you lose energy through
So
heat.
if it's less voltage, it's better?
No, if it's higher voltage, it's better. You want smaller amps.
But that was high voltage.
Yes, this is a much higher voltage. This is 1 million versus 50,000.
Oh, yeah.
So you want smaller amps, bigger voltage.
Yes, bigger voltage, smaller amps. I'm glad we're all on the same page. No, you want voltage to be as big as you can get it, because that makes the current as small as possible.
So you lose less.
So you lose less
By thermal
energy
energy.
through heat. Yes.
And less. Best sentence 2006.
It's gonna be the new these nuts.
No, it's not.
I know.
Okay. So let's assume that a transformer is 100% efficient. Okay?
That means no electricity. You can't have that.
You can't, but we're assuming we can.
Why are we assuming we can if it's impossible?
I will get to that. So we're assuming a transformer is 100% efficient. So exactly what power is put in is the same power that comes out, which is not the case. Most are designed with a 0.1% loss, which we talked about before. But we're going to assume it's 100% efficient, so no power is lost. So this allows for an equation for our power. So the power in the primary coil should be equal to the power in the secondary coil. Okay? So power, if we go back to here, current times voltage. So that means the current in the primary coil times the voltage in the primary coil should be equal to the current in the secondary coil times the voltage in
Oh,
the
I get
secondary
it now.
coil.
I get it.
I don't know.
Just look at the notes last time that you.
The power in should be the same as the power out.
Get it when it
Right?
goes like through the magnetic
This is the
coil.
formula for power, current times voltage.
Yeah.
So the current times the voltage in the primary coil should be equal to the current times the voltage in the secondary coil.
Oh, okay. But if it wasn't 100% efficient.
Yeah, in reality, that's not the case because it's 99.9%. But for what we want, we're going to assume this. Okay? See? Note this equation assumes no power loss. So we're going to stick with that for now.
Is
Is
it?
there an equation that
Is it VP?
Well, it's easily, well, not so easy because you can't guarantee it's exactly the same every time. But you could take this, or this one, sorry, times 0.999 because it's 99.9% efficient, and then get a more, or a slightly more accurate answer. But no matter what, it will never be perfectly accurate. So it'll be close, but not quite exact. Pretty much.
Will this be VP over VS equals IP over IS?
VP over VS. Oh, yes, I see what you're saying. So the primary voltage over the secondary voltage is equal to the secondary current over the primary current. Yeah, you could rearrange it that way if you want. So we have our formula here, so we're going to put it to use. So the primary coil of a transformer is connected to a 12-volt supply. It carries a current of 5 amps. If the output voltage is 240 volts, what is the current through the secondary coil? So I want you to use, I have my bat.
The caliber.
I want you to use this formula to solve this question.
Okay. I'll see what I can do.
So it is 12 times 5, right?
To start, yes. 12 times 5, yeah.
Wait, really? No, it's not.
Just
Is it?
100.
I thought it's 240 divided by 12.
That's only the first part. 12 times 5 is equal to something.
Yeah.
It's equal to 6.
True. But we're using the formula that was on the last page.
And then you do 60
IP times
250.
VP equals IS times VS.
No, you do 250 divided 240 divided 60.
Is it 1?
No, is it it 4?
What?
40?
Sure.
You're just guessing.
No, I'm not guessing.
He is.
No. I
Is it
divided what I
0.25?
got for that.
Yes.
Yes.
So remember,
Oh, I did.
IP times VP is equal to IS times VS. So we have 12 times 5, although those should be switched, equals 240 times whatever our current is going to be. So 12 times 5 is 60. And then I divide by 240.
And this formula is
Finding current or voltage. Okay. So that would be 1/4 equals the current in the secondary coil.
Cool enough.
So now we have several different formulas we've been given for transformers. Finding or how many turns are in each coil, finding voltage that way, current and voltage, power, current and voltage. We have several different formulas. It'll be your job when you get a question to know which one to use.
How do you know?
Depends on what information you're given. So if you're given 2 currents and a voltage, then you use this because you know you need that to find the other voltage. If you have number of coils and a voltage, you can use the other one to find the new voltage. If you give power and voltage, you can find current. So it really all depends. You see what you have and what they're asking for will tell you which formula you need to use. Mm-hmm.
4300.
Are there any questions? So this marks the end of chapter 21.
Yes!
No more